Some things in mathematics, as in most other fields worth of history, are just simply the consequence of somebody trying to do the right thing and a history looking back on it and finding a better way and us being stuck with kind of the interim. And that's exactly what happens when we talk about logarithms. Logarithms were given the name because they come from a very particular phrase. They come from logos meaning proportion, and arithmos meaning number. So we were trying to do a portion numbering system, and it was actually invented by a mathematician by the last name of Napier. And the idea being that if you take us back maybe to the 1700s, this was a time of enlightenment, a time of science, a time when many people were working through and discovering. And we can imagine that at a time of so much discovery, so much scientific research, there was a lot of data. And as it turned out, mathematics was required to make sure that science didn't get held up from the discoveries that they were seeking out. So if you imagine, let's imagine that we had a number of different decimals, I don't know, like 0.236 and 0.148 and 0.325 and 0.172. Let's imagine we had all these numbers, and based on our scientific research, we were needing to multiply them. Well, as it turns out, this is actually a very difficult computation to do. I mean, there's a lot of values, a lot of carrying that has to happen, and this is only with 4 data points. Imagine if you had 10 or 20 values instead. Well, as it turns out, though, if you could instead view this entire thing as addition, so let's imagine, obviously, that it wouldn't be the exact same problem, but let's imagine that there was something synonymous out there that would allow me to turn all of this into an addition statement of sorts, then we could see that this would actually be quite a lot easier to add on down. We could just simply add the columns moving across the page. And so this idea of taking things that were multiplication, moving it into a realm of addition was quite the accomplishment of Napier as he was trying to discover how to take these multiplication statements and move them into addition statements. And we'll talk about a little bit more about how this comes to be in the following lessons. But to understand this primary motivation, we can see why it would be such a valuable skill set. And it left us with this idea of logos arithmos. So logos arithmos, which nowadays we just simply refer to as logarithms. So logarithms were a very complicated method that involved a very long process that you can feel free to look up on the internet, but it took multiplication statements, moved them into addition statements, and it took hundreds of years for mathematicians to realize that what was going on here was actually exponents in disguise. And we'll explore that throughout this lesson. So let's go ahead and jump into the notes. So we're going to be dealing with logarithm functions, and let's begin with a little bit of the end in mind. Let's begin talking about this in form of exponents. So we'll start with a bit of a recall here, if we will. So let's sketch a graph of b to the x for b is greater than 1. Let's take a moment and remember what that means. So let's, if we go back to exponents, that's imagining that we have some kind of repeat type explosion. So if we said, for example, let b equal 3, then what we're talking about is that every time I start with 1, in the next iteration of this exponent, I would go from having 3 to the 0 as my initial to having 3 to the first. And that means that everything is exploding into 3 more instances. I've officially turned one thing into 3 things. And that would be my example of 3 to the first. So we have 3 to the 0th and 3 to the first. And 3 to the second, now I have 3 groups of 3. So that means that each of these has exploded into 3 objects. Each of these has exploded into 3 objects. Each of these has exploded into 3 objects, and that would be 3 to the second, 3 groups of 3. And you can see that right here, 1 group of 3, 2 groups of 3, 3 groups of 3. When we start getting into 3 groups of 3 groups of 3, then that means that all of these are now exploding, and I'm going to very quickly start running out of paper in order to express this thought. I might be able to fit in one more iteration, but by the time we get down to 3 to the 4th, I'm going to be running out of paper, and this is an explosion that happens very, very quickly. So let's talk about a table of values. What's actually happening? Well, if we start with to the 0th power, and we assume that we have something greater than 1, then something greater than 1 to the 0th power would be some b value to the 0th power, which we can again recall is just a way of thinking of b times b a certain number of times, and we could do as many times as we want. So long as on the bottom we still have b times b the same number of times, and then we get a subtraction of these exponents. So we're essentially viewing b to the 0th power as something like b to the 2 minus 2 power, as just an example, and that would be b times itself 2 times and divided by itself 2 times. So we'll put 2 on the top, 2 on the bottom, and that's going to come out to a value of 1. So that'll be our first coordinate value, is we can plot a point here at 0, 1, and that's a very common point for our exponential graphs. Now, if I talk about plugging in an x value of 1, that would be b to the first power. That's going to be equal to b just as it is. So we can go ahead and plot that value. That would be at a value of 1, we would get a height of b, wherever b turns out to be. And then if we come down here to 2, that would be b squared, which is equal to b times b. So that'll be our b squared value. This is our b to the first value. And so that's going to be b groups of b. And in fact, that's going to have a larger value depending on how big b is. That would be for a value of 2. And in fact, we can even select all of this here, and we can consider what happens if I look at a negative value. A negative value is going to be where I'm plugging in something, let's say, I don't know, negative 2. And negative 2 is b to the negative second power, and similar to what we saw in the b to the 0th power, that means that I have division by b 2 times. We can read this as a story. This is b to the 2 times of multiplication, but I've got, instead of 2 times of multiplication, I've got the opposite of 2 times of multiplication. So instead of b being multiplied by itself 2 instances, I've got b being doing the opposite of being multiplied by itself 2 instances. That would be b being divided by itself twice, or b being divided in 2 different instances. So that'd be 1 over b squared. And if b is greater than 1, this is going to be a number smaller than 1, so we get this kind of tapering off that occurs as we start looking at values that are more and more negative. So we got negative 2, negative 1, 0, 1, and we begin to get our standard exponential graph for values of b that are greater than 1. Something that has a horizontal asymptote towards 0 as we get closer on the negative x-axis, and something that explodes very quickly as we move to the positive x-axis. Well, what if we look at a b value that is, I don't know, let's say less than 1. So let's do a b value of, let's say, maybe negative 1. Okay, so we're going to need to start this a little bit differently. So now I'm looking at saying, okay, I would have, let's see, if I had something that was to the negative first power, we're going to have something that's actually completely different. Do I have something? How do we want to maybe phrase this one? Let's do, instead of b to less than 1, let's do b positive but less than 1. That'll help kind of frame our thoughts for a little bit here. The difficulty with the negative 1 is that it starts to become oscillating, where you've got, in every even power, you've got negative times negative makes a positive, but on the odd powers, you've got a negative outstanding, and we get what's called an iterative kind of sequence as we're bouncing down. But here, let's look at something that's just something like maybe b to the, or b is equal to 1/2. So what this means is that now, suppose we're starting with 4 objects, and that would be 1/2 to the, negative second power, because the negative would flip the 2 on top, and the second power would make it be the 2 times 2 gets me 4. Okay, now we can look at, okay, what would happen if I had 1/2 to the negative first power instead? Well, we can again view this as just being 2. It's like I'm flipping that reciprocal. So now I've got 2 instances collapsing every single time I iterate down. And now I could do 1/2 to the 0th power. That would be just 1. So again, we've kind of got this collapsing that's taking place as we're moving through. I could do 1/2 to the first power, and that would be when I have one object and it's kind of collapsing into whatever the next half iteration would be. I guess that would be a half object. And we could continue the pattern in from there. So now again, we get to look at and say, okay, well, -2, -1, 0, and 1 were interesting values. And for the work that we have to the left-hand side, 1/2 to the negative second power is the same thing as 2 to the second power, which is just simply equal to 4. Here I've got 1/2 to the negative first power equal to 2 to the first power, which we said was 2, and we get to see everything else as it flows on down. This would be 0, and this would be 1/2, as 1/2 to the first power and 1/2 to the 0th power. So let's play around with how this one looks out. Well, we can see, 1/2 to the 0th power would be 1. So that we do actually get, even again, that common value of 0, 1 does appear. 1 gets me 1/2, so now I'm going to be plugging that in right here, and we actually get this kind of flip where I'm looking at saying, okay, well at -1, now I'm up at a value of 2, and at -2, I'm all the way up at a value of 4. So it's like we've got this quick collapsing, or we can view it by simply recognizing that in this instance over here, we've essentially got the opposite, the reciprocal of 2 occurring, which happens with a negative exponent. So you can view this in one of two different ways. Actually, maybe this would be easiest to see if we had done this with 1/3. Let's change our situation real quick. Let's do it with 1/3. That would make all of these be 3s all the way through. That would collapse 3 objects down into 1 object, 3 objects down into 1 object, and 1 object down into 1/3 of an object. There we go. And we could adjust all of these values here as saying this would be 3, 3, 3, and 3. So 1/3 to the -2nd would be the same as 3 squared, which is 9. 3 to the 1/3 to the -1st would be the same thing as 3 to the 1st, which would be 3. 0 would be 1, and 1 would be 1/3. And so now we begin to recognize that it's really almost the exact flip of what we had above. Just take b to be equal to 3, and we're seeing that it's literally the flip happening this way. And it's because if I make my value down here a reciprocal, then it's the exact same thing as me trying to graph b to the -x, because this would be the same thing as 1 over b to the x. And we could look at this b to the -x as being the flip that occurs if I was to mirror image this entire graph across the y-axis. Just another way of looking at that one. Okay, what happens if b is equal to 1? So now we got b is equal to 1. Maybe I'm not quite sure what the diagram will be. Let's play around for a little bit. Let's do -2, -1, 0, and 1 again. So now I'm looking at 1 to the -2nd power. That would be, let's see, 1 over 1 to the 2nd power if I got rid of that negative, and that would still just be 1. -1 would be plugged in for the exponent, and 1 to the -1st power would again be 1 over 1, take that 1 and put it on the denominator, but that's not going to matter much, because that's just going to still give me 1. What about to the 0th power? That would be, let's see, 1 to the 0th power, would again still be 1, and 1 to the 1st power would again still be 1. Okay, so in this situation, we've got a nice horizontal line. So notice what we have when we're talking about exponents. If we are not working with 1, we either have something that is going to be collapsing very quickly by just continuously ratioing out, looking at a third of a third of a third of a third of whatever we started with, or I'm going to be exploding where I look at 3 times, 3 times, 3 times, 3 times, however much we started with, and we just continuously have this kind of growth, what we call exponential growth right here, or exponential decay, which we'll have right here. Okay, excellent. Now, when we were talking about how to solve out some of these problems, we did come up with a technique, just a little bit of logic that we were able to apply to this situation and say that if we are considering those diagrams, we can look at these problems where it's like 3 to the x equals 27, and we can view that 27 is nothing more than 3 times 3 times 3, which just simply means that 3 to the x is the same thing as 3 to the 3rd power. And through our diagram, we can again just kind of imagine what is that going to be? Well, that's going to be, how do I go to 3 to the 3rd power? I take one thing, I bring it up into 3 objects, I explode it into 3 groups, and then I explode those 3 groups into 3 groups. And then I would need to do that one more time before I had 27. Now, is there another way that I would be able to make this happen from my logic, from my story? Not at all. So it turns out that if I want to do 3 to the 3rd power, the only way to make that happen on the left-hand side is for x as well to be 3. I need 3 steps of this repeating to get to 27. So we can actually look at these as common bases to begin working through the logic if we don't know what the exponents are. So let's take a look at a little bit of a harder example. Here I have 8, and I have 1 over 16 to the x. That's a difficult one to look at. I really don't like that there's a fraction on the left hand or on the right hand side. So let's look at this as 8 equals 16 to the negative x. Notice that that negative exponent is just us recognizing I'm doing the opposite of multiplying by 16. So I'm going to do a negative to kind of show that within the exact same notation. I'm not changing the meaning, I'm just changing the appearance. Okay, well, what do I have that's common between 8 and 16? I could think to myself and say, what are some numbers I could repeat up to 8? I could obviously start with 8, but if I do one more grouping, 8 groups of 8 would not get me to 16, it'd get me to 64. I could do 2 and recognize that 2 groups of 2, or in other words, 2 to the third power, is a valid way of looking at 8. And similarly, 16 is nothing more than 2 to the fourth power, right? And you can think of that. That'd be 2 times 2 times 2 times 2 would be 16. So 16 can get replaced with all of that. We'll carry the negative x. That would look at a 2 to the third as being the same thing as 2 to the fourth to the x power. And now we can use our shortcuts we've discovered with exponentials to read this entire statement a little bit differently. If I'm going to repeat 2 4 times, and then I'm going to repeat it x more groups of that, then I can view this entire thing as just saying, well, I'm eventually going to have 4 times x as many of these repeats as we can. Let's maybe expand that out a little bit if that feels a little bit new. So we can view this entire thing as saying I'm going to repeat 2 to the fourth x times. So that'll be 2 to the fourth, 2 to the fourth, dot, 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 2 to the fourth, where however many times I repeat is x times. That's what this exponent means. It means repeat the multiplication of 2 to the fourth. And I can just count those up. That would be 4, and then 2 groups of 4, and then 3 groups of 4, and dot, 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 x groups of 4. So that's why we could rewrite this entire thing as 2 to the x groups of 4, or 2 to the 4x. Well, as we can see, this becomes a pretty simple problem from there, because then I just simply need to recognize that 3 has to be equal to the 4x, or that 4x has to be equal to 3, which means that x has to be equal to 3/4. Okay, very nice. How do we do a really hard problem like this one? Well, this is where we start to look at, again, we have a fraction on one side. I really don't like that, so I could write that as being 27 to the negative x. On the right-hand side, I can rewrite a lot of that as being 3 to the, let's see, a fourth root is the same thing as a 1/4 power. So I could do a 1/4 power to the x minus 2. But again, exponents to exponents, that would be 3 to the x minus 2 divided by 4 equals, and then on the left-hand side, can I get to 27 from 3? I think so. That'd be 3 to the third power. So it'd be 3 to the third power to the negative x. Okay, let's keep simplifying this until I get something just in the exponents. That would be 3 to the negative 3x equals 3 to the x minus 2 over 4, which would be negative 3x equals x minus 2 over 4 if I'm just looking at the exponents. And from here I can solve this problem quite simply. If I multiply by 4 on both sides, I get negative 12x equals x minus 2. I can subtract x from both sides. That gets me a negative 13x equals negative 2, and that would mean x would have to be equal to 2 over 13. Very nice. Now notice what it is that we're doing in a few of these problems. We're talking through the logic, but we're not actually writing it on the paper. Like, look at what happens right here. Here I jump from saying I have 2 in both of my instances to now saying that I'm looking at just the exponent. So there's a step of logic that we're doing here where we say we are trying to seek out just that power, what I'll refer to in a little bit as a power finder function. We're trying to really find out what that power is that makes this entire thing true. And notice it's the same thing that we did here, where we just simply recognize that I had x in a power and 3 to a power, so that must mean that my x has to be 3. And we even did it, let's see, right here, where we stepped in from saying I have a common base, so let me look at what the powers are only. So we're doing a step of logic where we're literally taking our attention from one thing and viewing it to another. But what if I don't have a common base? There might be a little bit of a desire for us to say, okay, well, that worked out very well because it just happened to have a 3 in the bottom, and the other worked out just well because it happened to have a 2 in the bottom. Is there another way for us to capture this model? As it would turn out, yes, but we'll get to that in just a moment. Okay. So, what are these logarithms? These logarithms, as it turns out, are actually just a method that Napier created to seek out these types of problems. How is it that I could take something that was, I don't know, exactly like we were working out above, and I said I have 2 to the third equals 2 to the 4x, and how could I simply perform some function of logic, some logic over here, and some logic over here, so that I could collapse all of this down to view just their exponents. Well, Napier called this a logarithm, right? From that logos arithmos. It's this thinking of trying to recognize logarithms. But today, it would be much easier if we just kind of viewed it under that same exponent guise as we've been talking about before. So here's what I'd like to propose that we do. Every time that you see logarithm for a little bit, let's just cross this entire thing out and write in power finder. Because that was really what Napier was trying to do, is he was trying to find a power finder function. So we could write that over here as saying, okay, what I'm looking for is a power finder where I am trying to find the power that takes 3 and gets to 81. Okay, and we could think to ourselves for a moment, what would be the power I would need to raise 3 to get to 81? And we could say, okay, well that would be 3 times 3 would be 9, times 3 would be 27, times 3 would be 81. That would be 3 to the 4th power, and that's really what we're talking about when we're talking about these logarithms, is we're just trying to say what is the power that takes 3 and brings it up to 81. So you have a couple of different options. We can either write this in the form of saying, well, I'm trying to find out this is 3 to the 4th equals 81, or I'm looking for the power finder. I'm trying to seek out the power that takes 3 and raises it up to 81. That's why we'll put the little 3 in the lower subscript there. We're trying to find out what power takes 3 and brings it up to 81. Well, let's do that for the next one here. We can view this entire thing as essentially saying, okay, let's cross this off and look at it as the power finder function. So it's the power finder where I have 4, and I'm trying to bring that up to 16. And we could ask ourselves and say, okay, 4 times 4 is 16. That's 2. That's a power of 2. So sure enough, that would be 2. Y must equal 2. And that's as simple as the answer gets. So logarithms are nothing more than it's trying to seek out a power that makes this statement true. It takes 4 and brings it up to 16. Let's take it with even some harder problems, and we'll see that it's really not any more difficult than what we've been working with before. We can cross this off and say, okay, all we're working with is a power finder function. So you could write this entire thing as just saying it's a power finder where I'm taking 3/5 and I'm trying to raise it up to x, and that would be equal to 2. Okay, let's think. What could we do there? We're looking for, again, 3/5 to the x. Right, we're trying to get x, so it's trying to raise 3/5 up to x, and we're being told that that power is 2. So let's do that. Okay, 3/5 is being raised to a 2. That's my power, and I'm saying that that's equal to x. Okay, well, sure enough, that would be 3 times 3 is 9, and 5 times 5 would be 25, so that must be equal to my x, and we're done. So we're doing a power finder function. Here, I already know what the power is, so we're trying to, again, make this statement true. 3/5 is going to be eventually exponential up to x, and the power used to do that is this 2. Okay, let's take a look at one more. Again, we're seeking out what the power finder is here. So this would be the power finder. We're trying to find the power that takes square root of 2 and raises it up to 1/4. Okay, so that would be what? Square root of 2 up to some kind of exponent here would be equal to 1/4. What would that be? Square root of 2. Okay, well that one's a little bit harder. What can I do with powers for that one? I could do square root of 2 times square root of 2. That would equal 2. Okay, so that would work out pretty okay. I guess I could then multiply it again. So I could actually do square root of 2 and square root of 2. That would eventually be 2 times 2 would be equal to 4. Okay, but I need to get it to be 1/4. So we could do a little bit of logic here and say, okay, well then I must not need to do it where I'm multiplying 4 times. I must need to do the opposite of multiplying 4 times, which would be 1 over square root of 2 times 1 over square root of 2 times 1 over square root of 2 times 1 over square root of 2, and sure enough, I think that would get us to 1/4. So what is the exponent here? I need to have an exponent that goes in here such that I am doing the opposite of multiplying 4 times. Well, that would just mean that x has to be equal to -4 then, because that would make the statement quite true. Square root of 2 to the opposite of 4 multiplications would be equal to 4 divisions, which is equal to 1/4. Okay, very nice. So so logarithms are nothing more than us seeking out those powers. Or, spoken another way, depending on what our unknown is, it's just the exact same kind of exponent problem we were working with before. So not too difficult. So let's now see. We've got this idea of exponents. It seems to be tied in with logarithms. Let's make this connection perfectly obvious. So again, let's take a look at some of this situation here where I've got an example of 2 raised to the x power, and I'm going to be changing x through. I'm going to be trying to figure out how this explosion happens, this exponential growth happens. So what happens if I plug in -2? That would be 2 to the -2nd power. That would be 1 divided by 2 times, so that would be 1/4, right? That negative exponent means the opposite of multiplying repeatedly, so that would be dividing repeatedly, that's 1/4. Okay, -1 would be 2 to the -1st power, that would just be equal to 1/2. 2 to the 0th power would be equal to 1. 2 to the 1st power would be equal to 2, and 2 to the 2nd power would be equal to 4. Okay, what about for our logarithm? Now I'm looking for log base 2 of 1/4. So I'm looking for what power takes 2 and brings it up to 1/4. Well, this is an exponent, so it means that I'm going to be taking 2, probably not repeatedly multiplying it, probably repeatedly dividing it, and in fact I'll be dividing it twice. So that would be -2. The exponent would be -2. If we wanted to write that in a different way, 2 to the -2nd power is 1/4, is the way of talking about this in terms of exponents. Okay, so sure enough, we've got the power finder for what I need to raise 2 up to get 1/4 would be -2. The power finder for what I need to take 2 up to get 1/2 would be -1. The power finder I would need to do to take 2 and raise it up to 0. Let's think through this one. I need to raise something up to a 0. Do we have that? 2 to the what power gets me 0. I don't think we have anything there. Right? 2 to the 0. No, hold on. Nope. 2 to the x equals 0. Let's go back and look at our graphs from before. Was there a time that if I raised any of these values up to any amount of groupings and ungroupings, I ever hit 0? No, up at the beginning, we talked about how there's a horizontal asymptote here. I never cause, whether I'm collapsing things and making them less and less and less, or expanding things and making them more and more and more, I never run out of dots. I just keep making those dots less and less or more and more. Okay, so that's an interesting kind of point. This one actually doesn't have a solution. There is not a situation where I will actually be able to plug in 0 into a logarithm. That would be asking me how many times do I need to repeatedly multiply or repeatedly divide so that I get 0. Doesn't happen. There's no way that I could continue to expand something or portion something out so that I got rid of it entirely. Okay, instead let's do log base 2 of 2. This is asking what's the power I need to raise 2 to get the number 2, and that would just be leaving it alone, so one instance. And then I could do log base 2 of 4, that would say how many times do I need to repeatedly multiply 2 to get 4? I need to repeat it twice. So let's now begin kind of plotting some of these on our graph. I'm going to call everything over here, let's do everything over here will be green. And we'll plot some points. So I'm going to have -1, -2, and that would be, -2 would be 1/4. And we're going to start to see that this is something that's very similar to what we were doing in our initial problem. In fact, this next one is going to be double that, this next one's going to be double that, and an intersection point of 0, 1. And then I'm going to be looking at doubling that to take it up to 2, and then doubling that to take it up to 4. And we get our nice exponential growth here. Okay, so that's the one that should be a given by now. Let's now talk about what it's going to look like if I try to plot this logarithm graph. So I'll use blue for this one. Well, the first thing I'm going to plot is at 1/4. 1/4 would go in right here. I'm going to go down to -2. So that'd be -1, -2. That'd be this one right here. Okay. At 1/2, that would be right here. I would be going to -1. So that'd be this point right here. So again, this is a question of what happens if I do a logarithm base 2 of 1/4, and we say that gets me -2. This is a question of what happens if I do a logarithm base 2 of 1/2, and that gets me -1. Okay, and then I could do, let's see, 2. I could do 2, which would be 1, 2 would go right here. and that would be a value of 1. That would be right here. I could do 4, so it'd be 1, 2, 3, 4 would go here, and then that would go all the way up to 2, and that would be right here, and we begin to get this graph. And we might begin to recognize that this is a very similar pattern to some of the graphs we've looked at before. Doesn't this look just like an inverse graph? Doesn't this look like something that was reflected across the line y equals x? Doesn't this look like something where all I've done is switched my questions and my answers? In fact, we've got a couple of those points right here in my green graph. Doesn't it look like, or isn't that exactly what I plotted, is that I had -2, comma, 1/4, and now down here I have 1/4, comma, -2? In fact, we can even check in. What would have happened if I tried to plug in 1 here? If I had tried to plug in a value of 1, that would be, what power do I need to raise 2 to get a value of 1? And we would say, well, anything, almost anything, raised to the 0th power would be equal to 1. So that would be 1 comma 0. And sure enough, that point appears right here. This would be 1 comma 0, which is the exact inverse of 0 comma 1. So we've proven exactly what we were talking about, is that this idea of switching our thought process, switching the way that we tell ourselves the story, seeking out the powers, is nothing more than doing the same inverses that we were playing with when we were talking about functions. We're just simply looking at the inverse. We're flipping the conversation and saying, what if I already know the answer? What is the question? And all that does is takes our entire picture where I was originally plugging in questions of x and getting out answers of y. It's like if I want to switch the question and the answer for my inputs and outputs, then I'm just going to switch the order of the numbers to reflect that change in perspective. Okay, interesting. So what kind of properties have we discovered from this? Well, first things first, log base b of b is nothing more than, again, the power finder function where I'm trying to say, okay, what power do I need to raise b to get up to b? And we've recognized that that's just simply 1. Right? And eventually we're going to try to move away from this notation and go back to the standard, but for right now it's sometimes a little bit more helpful. So we're looking for the power finder, we're trying to seek out the power that takes b and raises up to b, although that would be an exponent of 1. Okay, what about log base b to 1? Well, again, that's going to be our power finder. We're looking for a power finder function where I take b and I change it into a 1 using exponents. Well, that should be pretty clear that's going to be 0, and we can see that in the table above. What about this one right here? This one might be a little bit odd. Let's see if we can write it out with sentences. So it'd be log base b to the x would be, let's see, the power finder where I'm trying to take b and I'm raising it up to an x. We could think of that entire thing as saying, what exponent changes b to x? And then we can look at here and say that what we're doing in this problem is just taking b and raising it to that power. So it's take b and raise it to whatever exponent changes b to x. Okay. Well, isn't that a little bit odd? Like, let's think through that. When I'm looking for an exponent that changes b up to x, and then I'm taking b and I'm raising it to that exponent, isn't this entire thing just simply b to the x? Isn't that a much more simple way of talking about it? Take b and raise it to the exponent that changes b to x. Okay, so then whatever that exponent is, actually, no, that's a little bit different. It takes b and raise it to what exponent changes b to x. Okay, so there's layers here. There's a little bit more layers than we're talking about. We need to start framing our logic a little bit. So what exponent changes b to x? That would be, we could think of that entire thing as just being a new label. We could call that y. So we're saying that in this whole thing, we have log base b of x is going to be y, where y is whatever takes b and changes it into x. Okay, so then I've got this entire thing y, and I'm about to take b and raise it to y. Well, b raised to y is just x. So we can actually interpret this whole story a little bit more cleanly now. What is this entire thing saying with all of its nested in groups? It says take b and raise it to whatever exponent that changes b to x. Well, if I do all of this and I follow the instructions by the letter, then I should just be changing this to x, and x would be my final answer. It's kind of like I'm doing and undoing. This one takes a little bit to kind of work through the word riddling here, but we can take b and raise it to whatever exponent changes b to x. If you do this entire thing, it's the same, you're going to be left with x. That's what it says in the instructions. Take b and raise it to whatever exponent changes b to x. That means take b and raise it to an exponent that changes it to x. That means that if you do that, you get x. Sure enough. And we learn a lot of this in the form of rules when we're maybe learning this in other algebra courses, but in truth, this is just a little bit of a riddle. It says that if I put a logarithm in the exponent spot and the bases match, that it's nothing more than me just kind of skipping all the step and saying I'm taking b, I'm raising it to a power, but then I'm choosing that power such that my end result is always x. Well, then just skip the middle and go straight to the answer. This just simply says you have done and undone your exponent logic. You've taken b and raised it to something that effectively undid it and brought it back down to x. Then sure enough, log b to a log base b is nothing more than us just ignoring all of this middle and getting the x as the end focus. Kind of an interesting little riddle there. Let's talk about how that works out when we're looking at this one here. Log base b of b to the x. Okay, so that means what? What exponent, because we got our power finder function, right? What exponent raises b to b to the x? Well, can you see what exponent takes b and puts it to look like b to the x? Again, this would just be x. That's exactly what this says. Again, read it over. What exponent raises b to b to the x? X does. It's the exponent I need to put in here to make b up to b to the x. So again, we've got this just undoing and redoing in different ways, depending on the scenario we're looking at. Either taking exponents, taking things and raising them to the value that eventually gets me to x, or here I'm asking a question, what exponent do I have to be using in this situation? But the takeaway we can use for shortcuts to help kind of get our mind wrapped around this as we work through practice problems is that we're really just simply saying that if I take log base b of something where b is the base again, I'm really just pulling out that x as the only focus. They kind of cancel each other out as being the opposite and inverses of the logic. And here, the exact same thing. If I take b and I raise it to an exponent of log base b, then again, I'm just kind of undoing both of those steps of logic, and I'm leaving myself with the x. This one's a little bit of a fun riddle. Give yourself time to think this one over. So let's look through a couple more of these examples. Let's do log base 3 of 3 to the 4th. So again, we're asking ourselves, there's a power finder function. So what exponent takes 3 from down here, and gets 3 to the 4th? Well, sure enough, that'd just be 4, wouldn't it? These are simpler than I thought. What do I need to use to take 12 and raise it up to 12? This would just be 1. And you can actually view this one a little bit differently. Imagine that this was just 12 to the first power. I haven't changed the meaning, I've just changed the perspective. But can we see that again? It would be of the correct structure that I could cancel out the 12 in the base and the 12 inside of the logarithm. They're kind of pairing us up and recognizing that all I'm doing is saying what exponent takes 12 and raises it to 12 to the first. That'd be 12 to the first. Okay, what about this one right here? So I've got 7 to an exponent where the exponent was chosen to be to the exponent which takes 7 to 13. Well, 7 raised to an exponent that takes 7 to 13 would be 7 raised to that exponent so that I get taken to 13. I would be left with 13 again. So we can view this entire thing as that essentially just crossing away and me being left with the 13. Interesting little logic puzzle there. All right, here. Let's see. 8 to the first power. So we're looking for what power takes 8 to 1. Well, I could use a positive number like 1. That would be 8 to the first. Second, 2, 8 squared. I'm going in the wrong direction. What about negative numbers? 8 to the negative first, that'd be 1/8. 8 to the negative second, that'd be 1/64. No. Somewhere in between there. 8 to the 0th? Oh yeah, sure enough. 8 to the 0th, because anything other than 0 raised to the 0th power does in fact get us 1. So there we have it. This entire thing would be equal to 1. So we get to see that what we're doing is just kind of taking us from one exploration into another exploration, changing our perspective, working through the logic, and getting some answers that result. But before we get too far, I do want us to take a look at a different way that we could view logarithms, one that I kind of think is sometimes a little bit easier. So let's now give ourselves a little bit of a break from the perspective of the opposite of exponents, and let me introduce you to this idea that I like to call the fake logarithm. Not a real mathematical one, but a fun little riddle for us. Consider the following fake logarithm, or what I'll call a flogarithm. So a flogarithm, I'll write it with f log. The flogarithm, what it does is it just counts as zeros. So let's take a look here, for example. What would the flogarithm of this be? So let's look over here and we'll say I'm looking for the flogarithm of 1. How many zeros do we see? I see 0 zeros. We'll call that 0. What about the flogarithm of 10? How many zeros do you see? I see 1 0. We'll call that 1. And we could do these with all of them, right? So the flogarithm for the next one, flogarithm of 100 would just be 2. And you're all looking at me going, this is incredibly easy. I don't know why we're trying it, because the flogarithm of 1000 would just simply be 3. And then the flogarithm of 10,000 would just simply be 4. Okay, so that's our flogarithm. Now, with this in mind, because I did say it was a flogarithm, I said it's a fake logarithm. I actually didn't tell you all the details. And true enough, for numbers that start in 1, the flogarithm does take this and bring it down to just counting the zeros. But in truth, you don't just have to start with numbers that have 1. We're curious, what would happen if I did the flogarithm of 2000? Now, 2000 would be some number that would fall somewhere between 3 and 4. So somewhere in here would be the flogarithm of 2000. And so we could guess at what this might be. It's maybe a little bit closer to 1000. It's maybe not quite close enough to 10,000. So somewhere in between 3 and 4, we can maybe say this is going to be what, 3.1, 3.2, and we could put a pretty good guess on what this is. Now, as it turns out, this flogarithm, or the counting zeros after a 1, it is actually something that we refer to as log base 10. Now, I disguised it for us, but let's take a moment and connect the dots here. Log base 10, again, asks us, it says, what do I need to raise 10 to get to a value of whatever? To get to a value of 1, I would raise it to a 0. To get to a value of 10, I would raise it to a value of 1. To get to a value of 100, I could get it to a value of 2. What about to 1,000? I could raise 10 to the 3rd power. 10,000 would be 10 to the 4th power. What value do I need to raise 10 to get 2,000? That's not going to be a clean number. It is going to be a decimal, and in fact, if we plug it into our calculators, let's try it out. As it turns out, our calculators will have this as a default logarithm, so even if I pull over the one from my computer, it's just this log right here is a default log base 10. It's this flogarithm, and we'll explain why that is in a moment. But let's just do, if I have 2,000 here, I want to do the logarithm. Okay, sure enough, a 3.3. I guessed 3.1. 3.3 still makes sense to me, somewhere between 3 and 4. So we can put that in. Okay, so it's 3.1. No, it actually was something more like 3.4-ish. Okay, so what is it that we're doing with this logarithm? We're just counting up from 10. Why would we be giving this something so particular? Well, as it turns out, most of the Western cultures count nowadays in base 10, and that's for reasons that are pretty obvious to us when we begin counting. We count on our fingers. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 fingers, and so we count in tens, and every time we run out of our digits, we move up into the next place value. And so that's why I step up from 1, which is just using 1 digit, to 10, which uses 2 digits next to each other, to 100, which uses 3 digits. So it turns out that this log base 10 is our way in a Western culture to recognize that all we're doing is stepping up to needing one more order of magnitude, one more digit, one more place value to express what it is that we're talking about. Now, this might feel like something that doesn't come up very often, but it comes up all the time, right? So this log base 10, as it's referred to, is actually more often just simply referred to, as we saw in the calculator, just the standard log. So we'll call this log x. So if we ever see it without the 10, it's because we're assuming that the way that we're counting is in the same way that we normally are counting in our Western culture and using these digits. We're counting in bases of 10. And this is actually something that's much more prevalent to society than you would have thought. If you look at the decibel scale and actually break that down for a moment, right? So let's look at decibel scale. This would be our decibel scale. Hidden within this name is deci. This is 10. This is another way of saying 10. So it's our 10 bell scale. It's our way of organizing sound into magnitudes of 10. And we can begin to see that this idea of just like stepping up here from our logarithm of saying that this is 10 times more than this one, which is 10, or than this one, and the next one is 10 times more, and the next one is 10 times more. So every time we take a step up, we're not stepping up by a value of 1, we're stepping up by 10 times what we had before, which is an explosion. This helps to make sense of the decibel scale, because in the decibel scale, we can view that between a whisper and a normal conversation, there are 4 steps, or 40 decibels, as it's written in this scale. There's a little bit of a convention change there, but we can see that there's 4 levels of magnitude. I go from a -10 to a -6. There'd be 4 steps in my model, in my diagram. But if I go 4 more steps from that, I start getting into something that's closer to the threshold of pain. And if I go 4 more steps from that, I start to get into something that is closer to, above a pain. This is something that is deafening, a jet taking off. So we're starting to recognize that as we are stepping up, each of these steps becomes increasingly more in terms of magnitude, right? So let's now go from there. Let's look at earthquakes. So for example, the earthquakes are another time when we have a log base 10 scale. And it's because we're trying to measure things that can be very, very small as well as very, very loud. And so we get to recognize that if we are looking at something that is let's say an order of magnitude 7 earthquake, which is strong, that might just be 2 steps above a very small earthquake. But if you go 2 steps above a magnitude 7, you are in one of the great earthquakes of history. So these steps up are not talking about just simply being 2 bigger. So if I talk about a magnitude 5 earthquake versus a magnitude 6 earthquake, one is small, one is still not very much damage. If you talk about a 7 compared to an 8, you're talking about something that's going to, maybe damage a city to something that could damage a country, right? Or a small country, an island. We're looking at something that could affect New Madrid, that could affect Alaska as a whole. We could look at something that's affecting San Francisco in 1906. These are some of the great catastrophes that we're working with. So not to say that these necessarily are countries, but there have been plenty of times when earthquakes of this magnitude have shaken entire countries like Haiti, right? So what is it a nice way to refer to this one? Well, we can think of like a magnitude 3 earthquake. It has the same destructive power as a lightning bolt. And this isn't to say that lightning isn't destructive, but if you look at a magnitude 3 earthquake and compare it to lightning, if you look at a magnitude 5 earthquake, this can be referred to as the same strength as the atomic bomb. And we can all agree that this is a significantly different level of destruction. One can obliterate a city, the other may obliterate a house. So again, we've got something that's very, very much more intense as we step up. It's taking advantage of this explosion nature and trying to capture it as just simply saying, what does 1 step mean? Now 1 step doesn't mean +1. Now 1 step means 1 more order of explosion. And the pH scale is another example. We can go from a pH of 5, which is coffee, something that I drink every day, to 3, which is orange juice, something that is actually significantly more acidic. You can test this by actually taking pennies and putting them in orange juice, and they will make them shiny. But if you go from this 5 to this 3, we're not talking about too much damage. You go up 2 more levels from 3 to 1, and you're talking about gastric acid, one of the most damaging acids on the planet, right? Something that's hydrochloric, something that is known to be able to dissolve just about anything that you put in it. So, interesting places where log base 10 pops up because it's just our common way of talking. How do we talk about something that's 10,000 versus 100,000? It's just 1 more order of 10. So for this reason, again, as we said, we're going to call log base 10 our common logarithm, just because it is one that comes up a lot, because we do talk about things as being multiplied by 10 whenever we want to talk about it as being one order higher. We'll call things the natural logarithm if it is a log base e. And we talked about e when we were working with our exponents. This is very commonly used as an upper bound for our continuously compounding interest. And because it comes up quite a bit when you're talking about any kind of exponential growth, whether it's in finances or whether it's in natural systems and population growths, this gets its own title as well. And we refer to this as ln, the natural logarithm, or the logarithm naturale, which is based on how it was originally titled. So different language, different order of the words. But let's use these in a couple of problems to get a hang for it. So if I just see log 10, I can rewrite this entire thing as just saying, really, this is log base 10 of 10 equals 1, which again, if you want to think of this more differently, I'm looking again for that power finder function that says, okay, I have 10, I'm trying to raise it up to 10. What would make sense to be the exponent? That power would make sense to be a value of 1. Okay, what about this natural logarithm? Let's rewrite it. Natural logarithm is log base e. It's that number e that's a little bit more than 2, right? And we could say, okay, this is log base e of 20 is equal to z, which again, I could rewrite this as saying, this is that power finder function of saying, what do I need to raise e up to get 20? Well, that also gives me another way of changing my perspective on it. I'm trying to find out, what do I raise e up to get 20? And we can actually do this in our calculator. It's not an easy calculation to do by hand, so calculators are preferred. And we could just simply say, okay, if I was looking for natural log of 20, then let's type in our 20. I'll do the natural log of it, and you can see it's about 2.3-ish. Okay, 2.3-ish. But again, if we remind ourselves of what e is nothing more than 2.718. And so we can test this. We can actually say, okay, if I have 2.718, I'll clear everything. So let's do e. And we'll check and say, okay, what happens if I was going to raise e to a power of 2.3-ish? I would expect to get something that's about 20. Oh, this one's off a little bit here. Let's see what we did. Oh, it just simply copied it wrong. And actually, let's do this again. Natural log of 20. Natural log of, oh, see, I can't do natural log of 0, just like we saw before. It actually even bothers the calculator. So we'll do 20. Natural log of 20 is 2.9. I wrote it down as 2.3. Let's change that. So it's 2.99. And I can actually check 2.996. So just about 3. And so let's clear this all out and remind ourselves that, again, e is nothing more than 2.78. It's just a constant. And let's try it. Let's raise it to the power of just about 3. Let's raise it to 2.996. We should expect to get something about 20. There it is. Something's just about at 20. A few more decimals would have made it even more accurate, but that's pretty close. We get the idea. Okay, what about this one right here? Let's rewrite this. This is log base 10 of x minus 1 equals t. So we can think of this as saying I need to take 10, I need to raise it to some kind of exponent so that I get x minus 1. And sure enough, that's exactly as far as we're going to be able to take it. I don't know what t is. I don't know what x is. I could mix and match them to solve for them differently, but we get the idea. All that I'm talking about right now are all of these different ways of expressing the exact same thing. So let's see what things we can evaluate without the calculator. Whenever we're asked to evaluate with them without the calculator, that means there's a little bit of a riddle that we're trying to follow on here. So again, what do we have here? This would be log base 10 of 100. I'm looking for, what do I raise? What's the power that raises 10 up to 100? That would be 2. Easy peasy. Here, natural log would be log base e to the square root of e. So I'm looking for what exponent is it that's going to take e and make it into square root of e. Okay, well that seems a little bit weird. Maybe I'll rewrite that. Logarithm of e that takes this entire thing to make it e to the 1/2. That's another way of thinking of square root of e. And then sure enough, what's the power that makes this whole thing happen? 1/2. So nice way of us kind of doing the logic for this one. What about this one here? E to the natural log of 51 can be thought of as e to the natural log, which is just log-based e of 51. And so again, we're saying, what is the exponent? This right here is just going to get us a power. It's a power finder function. So this is going to get us a power such that e gets taken up to 51. And then whenever I have that, I've got e to whatever that power was that takes me up to 51. Well, then that's just going to get me to 51, right? You can think of this entire thing as just kind of covering it all up, getting the logic idea is saying this is just simply a power, whatever that power is. And when we apply e to that power, we will get up to 51. A little bit of a logic riddle there, kind of fun. Let's talk about the domain real quick, because it'd be a shame to leave that one alone. How do we graph this entire thing? Well, notice I have the natural log, that's just log based e, of x plus 2. I've got a negative sign here, and I have a minus 1. So let's think of a way that we can maybe expedite our graphing process. We know that the graph is going to be something along this line, because remember, it's going to be the inverse of an exponential that goes like this. So we know that's going to be somewhere around that curvy shape. What are some easy values? Well, can we remember what happens here when I plug in 0 for x? That'd be plugging in 0 for this value here and asking ourselves, okay, e to the what power gets me... Oh, no, that's not quite right. Excuse me. I'm plugging in a value of 1 here. There we go. E to what power gets me 1, that'd be a height of 0. So this is going to be 1 comma 0 normally, but this is, if I would plug in, when would I get that if I plugged everything in? That would be when x is equal to -1, right? Okay, so hold on. Maybe we'll make a table of values. We'll organize our thoughts. Too much going on here. Okay, so let's think through what is that we're actually doing. Interesting points. I'm interested as to what happens if I plug in -2. That just seems to be a point that stands out to me. So I could ask myself and say, okay, that would be negative log base e of -2 plus 2 would be 0 minus 1. And I could ask myself, okay, what power takes e up to 0? And we catch ourselves in that loop again. I can't have an exponent that raises e or anything up to 0. So that actually doesn't exist. No value at -2. So I can actually go over here to my graph and plot in -1, -2, and I'll put a dotted line, a vertical asymptote, as a visual reminder that there's not going to be an answer there. Okay, what about -1? If I plug in that would be negative log base e of -1 plus 2 would be 1 minus 1. So I'd be asking myself, what power takes e and raises it up to 1? That'd be a power of 0, so it'd be -0 minus 1, which just gets me -1. Okay, so -1 comma -1 is going to be a point. Interesting. All right, what about, let's see, if I plugged in 0, that would be, let's see, log base e to the 0 plus 2, that'd be trying to figure out what do I need to do to raise e up to 2. I don't know that I like that, right? Negative log of e to the 2 minus 1. I don't know what exponent takes e and raises it up to 2. Maybe the next easiest one would be to just plug in e. That'd be negative log of e to the e minus 1. And I know the exponent that takes me from e up to e would just be 1. So that'd be -1 minus 1 gets me -2. Okay, so I can plot that one. That's going to be 1, 2, 3. E is somewhere in between here. So here is going to be my e value right between 2 and 3. And if I plug in e, I should get a -2. So -2 would be right here. Oh, and now I recognize what's happening. I've got a vertical asymptote. I've got a little bit of a curve here. I think we're going to have something that looks just like this. Where am I seeing that? Well, a combination of two different places. I've been thinking about this one and how it looks a lot like what we're doing is just a transformation in my mind. So maybe let's take all of this and try this from just a transformation now that I've got my mind made up. What am I actually doing here? I could think of this first as plotting natural log of something much more simple. Like, let's just do natural log of x. Natural log of x is going to be something that intersects right here, where I have 1 comma 0. And then, as we saw before, I kind of have this ripple up this way, and then this ripple down this way, just like that. That's from back in the beginning of the notebook chapter. What am I doing since then? I'm doing x plus 2, which shifts my entire coordinate system back 2. So I can actually do that. I'll move my coordinate system so that the x values go up a little bit. That would change this to be 3. Did I do that right? No, I am adding 2 to my exponents, or to my x values. Okay, my mistake. I originally had it where we had this as a 1. x plus 2 means that I'm actually taking all of my x values and adding 2 to it. Okay, so I'm actually going to be stepping this reference axis all the way up over here, which means this value has changed from 1 comma 0 to negative 1 comma 0. There we have it. Okay, so that's the first transformation of when I change this from natural log of x to natural log of x plus 2. Okay, good. And then I have still that same vertical asymptote. It's just that vertical asymptote is now at negative 2. Okay, from here, what's the next transformation we could do? We could make it negative natural log of x plus 2. Well, sure enough, that's going to be plotting it on this exact same point. But now I'm going to be going through here. We'll flip this entire thing like this. And this would be the negative of that graph. And then all I need to do is shift everything down by 1. So when I come over here to my final graph, what was at negative 1 comma 0 is now going to be at negative 1 comma negative 1. And I should get just about the exact same graph, just shifted down. We'll put in my vertical asymptote, negative 2. I know that it's going to kind of ricochet off this way. Let's graph it in carefully. And it should be something just like that. Okay, so my nice transformations still work the same way as we did it before. If I add 2 to an x value, that just simply means that I'm shifting all of my coordinate system to the right 2, which effectively looks like I'm taking my graph and shifting it to the left 2. Okay, if I make a function negative, that just means that I'm taking all of my negative heights and making them into positive heights. And if I subtract 1 at the end, that just simply means that I'm taking my final height, but I'm taking 1 away from it before I plot it. And so this would be a nice way for us to view that final picture we have, with negative 1 comma 1 being a nice reference point for us. Okay, so what's the domain? Well, as we've recognized before, if I am looking for values, natural log here is saying what are the values that I could plug in here such that it'd be e to some unknown power. If this was equal to y, it'd be e to some unknown power y gets me x. And as we saw in our diagrams, this is nothing more than taking values and splitting them up in the case of exponential growth, or in the case of exponential decay, collapsing them on down. So what are the values that I would not be allowed to have in here? I would not be allowed to have any kind of 0 value, because as we talked about before, if I am exploding or I am collapsing, I can't get rid of things entirely. 0 would not be allowed. And you're never going to get any negative objects from this kind of model. So we begin to recognize that the domain of any kind of logarithm function, and we'll write ourselves a little bit of a note here, is that the domain of log base anything, we'll call it log base b of x, is x has to be values that are greater than 0. Why is that? Well, because the only thing that goes along with our story, the only things that I could possibly raise b up to are going to be positive values. And that's going to happen from collapsing, doing a lot of portioning, or growing, doing a lot of expanding. But I can't collapse everything entirely. I can't expand everything to get to 0, and I can't expand or collapse to get to negative objects. So the only answers that are valid are positive numbers that I could expand or collapse into. Well, how do we do it for this function that we just had above here? I'd be looking for the only time that I could have some difficulty, and that would be when natural log of x plus 2 has a value being plugged into here that is not satisfying a greater than 0 result from my exponents. So when did we have problems with this one? Well, we'd have problems whenever x plus 2 is less than or equal to 0. So in other words, x plus 2 has to always be greater than 0, just like in my log base b example, x had to be greater than 0. And that's going to naturally imply then that x has to be greater than negative 2. So how can we tell out when these things are going to have trouble? We need to be looking to make sure that we're only putting in positive answers into our logarithms, because those are the only things that make logical sense for us to be able to expand or collapse into logical amounts of things at the very end of that process. How do we do it for an example like this? This would be log base 7 of 2x minus 5. Well, again, as we recognize, this is a story where I'm saying, what can I raise 7 up to in terms of quantity, or what can I portion 7 down to in terms of quantity? And I'm never going to be able to portion this so that the inside is negative, so we'll just make this inside have to be positive to keep the logic true. And sure enough, that's going to be 2x has to be greater than 5, which means that x has to be greater than 5 halves. Excellent. And I'm going to leave this one for you to practice on your own if you would like. Now, the one thing I'll remind you of is that if you're working through a problem like this, where we say 2x minus 1 over x plus 3 has to be greater than 0, that we're not just simply looking for when is it 0, we're actually going to have to solve this thing using a number line. And I'll leave it to you to try to remember when is it that we would place different values on this number line to help represent to us when this fraction, this rational expression, when this rational expression could switch from being positive to negative or vice versa. Those would be the values that we would plot on the number line. We would choose some test points for the in-between to see how this fraction behaved between those zeros or between those undefined values, and then we would describe our answer using interval notation. But that's about it. So logarithm is nothing more than us asking the question of what is the exponent that would raise my base up to my result, and they're easiest thought of as a power finder function, or easiest thought of as how many times do I need to repeatedly multiply to get to this result. So if you have any questions, call me over as always. Wish you luck. Very, very fun idea, very practical applications if you know to look for them.